So should we start then? I think
Yes.
Dr. Devashish Haldar from ISAR Kolkata, I just contacted him and he said it will take a couple of minutes for him to join. So hopefully he will join during the process. And then with your permission, kind permission, sir, we are starting then.
Okay, start.
Okay, thank you, sir. So I'm Dr. Taposh Ghosh, Assistant Professor. Hello.
Just one request, those who are not speaking, if you could kindly keep your microphone on the mute, that helps.
তাপসের তো মাইকটা মিউট দেখাচ্ছে, তুমি কি মোবাইলে বলছো নাকি? মোবাইলটা বন্ধ করো, কম্পিউটারে চেক করো।
মোবাইলে তো মিউট নেই, আনমিউট করা আছে স্যার।
না, তোমার এখানে ল্যাপটপে
Sir,
আনমিউট করা।
Arijit sir, sir, echo is coming. Arijit sir. It is now fine, sir.
হ্যাঁ, দুটো করে
I
চালিয়ে
think
দিছো।
it's okay now, sir. I think now it's fine, sir.
Yes.
Okay. So I think now I'm audible, sir, right? Okay.
Sir.
So yeah, so just let's begin that I'm Taposh Ghosh, Assistant Professor of Department of Applied Science, Makaut, West Bengal. And on behalf of the organizing committee of this webinar, a very welcome to all the esteemed panelists and participants to this webinar today. And I'm very much thankful for all the attendees who took their precious time to join the webinar on smart nanomaterials for applications in applied sciences. Now, of late, the innovative research ideas at the interface of chemistry and materials are highly encouraged by almost all the research funding agencies in India, as we know. And our Honorable Vice Chancellor, sir, has always been emphasizing for the same and inspired us to stride on the thirst of innovative research areas and proposals. And also he granted the research seed money for young faculties coming up with the new ideas. And in fact, in designing the courses in our in-house PG programs like MSc in Applied Chemistry or MTech in Material Science and Technology, to name a few of many, we take into account to transmit this concept to the students as well. And genuinely, I truly believe that all of us will be highly benefited out of this webinar today, and there will be a lot of knowledge to take away at the end of the webinar. Now, before I proceed further, let me take the opportunity to introduce our today's sterile line of speakers and panel members. Today we have with us our Honorable Vice Chancellor, Sir, Professor Dr. Shoykot Moitro, and Professor Dr. Shukhendu Shamazdar, Director, School of Natural and Applied Sciences, Professor Dr. Radhavallabh Bhatt, Head of the Department of Applied Sciences, Dr. Arijit Bagh, Associate Professor, Department of Applied Sciences, and of course our distinguished eminent speakers, Professor Dilip Kumar Maiti, Fellow of Royal Society of Chemistry from Department of Chemistry, University of Calcutta, and Professor Devashish Haldar of Department of Chemical Sciences, Indian Institute of Science, Education and Research, Kolkata. Now, with this brief introduction of the panelists, may I request our Honorable Vice Chancellor, Sir, to inaugurate the session and deliver his inaugural speech. Sir, please. Sir.
Tapos, did you call me for saying something?
No, sir, I didn't call you right now.
Okay.
Sir, just
We are waiting for your keynote speech, sir.
Yeah, sir, we are waiting.
Dr. Shamazdar, kindly continue.
Okay.
Dr. Shamazdar or Dr. Can you continue?
Okay.
I am joining.
All right. Thank you. Dr. Ghosh, then.
Yes.
Shall I?
Sure, sir. With pleasure. Please, sir.
Honorable Vice Chancellor, distinguished speakers and panelists, fellow colleagues and members of the boundaryless knowledge community. Namaskar, namaste, good day. Allow me to a bit of digression this morning. Spare me the indulgence of drifting to the domain of philosophy of science. As scientists, when we study the world, both non-living and living, we see, rather, we realize a few overarching principles at work. Let's identify those principles. The first one is assembly or organization. Small particles, subatomic particles, assemble and organize themselves into atoms. Atoms organize into molecules, molecules into matter, maybe rocks, matter into planets and solar system and the universe. So this principle of organization is there. I gave example of the inanimate world, but in the living world, cells organize into tissues, tissues into organs, and organs into organisms, organisms into society. So that is the first principle that we take note of. The next one is order. That means having the particles organized in such a way that they occupy distinct and specific position in space. So there could be long range order, there could be short range order. So if it is a long range order matter, we typically call it crystal. If there is no order, then we typically call it amorphous. And liquids, of course, do not have long range order. So examples of those abound as well, such as silica. So silica and silicates, they pretty much make up the whole solid planet, the crust of the earth. On the other hand, those are mostly crystalline. On the other hand, we have amorphous form, which we call glass. One thing to be noted in this context of order is normally nature provides geological time, astronomical time, and it provides a decent amount of temperature and energy as well. So naturally abundant materials typically tend, if in solid form, they typically naturally abundant solids typically tend to be in crystalline form or ordered form. The next principle that we observe is that of scale. Scale may be both in space, that is spatial scale, and in time, that is temporal scale. So temporal scale, for example, could be very small. I mean, the human level, these are seconds and minutes and hours and days and etc., etc. In geologic scales, these things really, these are blips. So for geological events to take place, it takes thousands of years, at least millions of years most of the time. And for the cosmological level, it takes billions of years. In space, also, we find scale play a very important role. For example, in atomic scale, then atoms get together, subatomic particles get together, form atoms, form, again, hierarchically, they go up and form molecules to matters. So that is a crucial thing to observe, because it is not for the sake of scale. It is not that something is the human scale meter, something is millimeter, something is micrometer, nanometer, or below pico, femto, and growing larger on the other direction as well. Natural laws, the laws governing the behavior scale in the human scale, it is the classical and Newtonian mechanics that prevail. While at the smaller scale, atomic, subatomic scale, it is quantum mechanics that prevail. So we have organization or assembly, we have order, and we have the principle of scale. Then comes the principle of hierarchy. What it means that in the process of organizing or assembling, organized units act as the building block for the next higher scale. To give a silly example, say sand grains or clay, they could be organized into form bricks. The bricks could be assembled. They act as a building block for making walls. The walls act as a building block for making rooms. The rooms act as building block for building houses. Houses act as building blocks for making housing complex, and housing complexes act as building blocks for making cities, if you will. And it could be generalized. I gave the example of the cells organizing hierarchically into tissues, tissues into organs, organs into organisms, and organisms into society. Now, this hierarchical organization leads to the other principle, very important principle, which is that of emergence. Now, the principle of emergence observes that certain properties emerge out of assembly and organization of the constituent particles. For example, weather we can study locally. However, it is exceedingly difficult, if not impossible, to predict, because the weather materializing somewhere is an emergence property. So with emergence, there is associated concept is that of unpredictability. There is a sense of wonder that, oh, this is what's happening. Then another emergence property is life. We can analyze at the lower level at different scales, but it is impossible to pinpoint where the seat of life lies. And in different organisms, the life is actually centralized or decentralized to different extents. For example, plants, life is extremely decentralized. Many parts of it could be chopped off, yet life continues. Then finally, one very good example is that of the property of liquidity of water. We can know all about subatomic particles. We can know all about the atoms, the element hydrogen. We can know all about oxygen and how the Mickey Mouse type looking molecule with two oxygen atoms and one hydrogen atom making the H2O molecule. However, when zillions of H2O molecules come together, then only the property of liquidity of water emerges. It cannot be predicted. So we have the principle of organization, order, scale, hierarchy, and emergence as the generic principles when, as students of science, we can observe. Now, there was a person who put together this idea in a rather illuminating, articulated, cogent fashion in a very famous paper published in 1972 in the journal Science. But before, in order to appreciate the impact of that paper, we need to rewind a little bit and get to the history and the prevailing scientific culture of early 20th century until 1970s. There was if I may use the word, there was a culture of scientific arrogance, of thinking reductionism not as one of the ways of understanding science and the world, but the way to understand the science and the world. And these were promoted by very famous people like Victor Wiscoff and Murray Gell-Mann. And the idea essentially was a derogatory dismissal of the rest of the science other than subatomic and particle physics, a derogatory dismissal of everything else as chemistry. Now there was this person, Phil Anderson, who focused his brilliance on this issue. He was incited not just by the fact that he was a condensed matter physicist, and Murray Gell-Mann openly referred to condensed matter physics as dirty work. Well, there was an emotional side, but there was a very deeply realized, profound side of his work about this property of this principle of emergence. So I would quote actually a few things directly from this paper. To begin with, Phil Anderson says that he first has to admit there is a philosophically correct form of reductionism, namely a belief that the universe is governed by natural law. The vast majority of working scientists accept that assertion wholeheartedly, says Anderson. Indeed, it is hard to imagine how science could exist if they didn't. To believe in natural law is to believe that the universe is ultimately comprehensible, that the same forces that determine the destiny of a galaxy can also determine the fall of an apple here on Earth, that the same atoms that refract the light passing through a diamond can also form the stuff of a living cell, that the same electrons, neutrons, and protons that emerged from the Big Bang can now give rise to the human brain, mind, and soul. To believe in natural law is to believe in the unity of nature at the deepest possible level. However, and that's a big however, says Anderson, this belief does not imply that fundamental laws and the fundamental particles are the only things worth studying, and that everything else could be predicted if you only had a big enough computer. A lot of scientists certainly do seem to think that way. Back in 1932, as I pointed out, the physicists who discovered positron and the antimatter version of the electron declared the rest is chemistry. More recently, Murray Gell-Mann himself had been known to dismiss condensed matter theory as dirt physics. But that was precisely the kind of arrogance that Anderson found so infuriating. As he wrote this article, which is titled, "More is Different." This is a profound title of a paper. You cannot remove a word. You cannot make a sentence with less than 3 words. This captured a lot of significance. More is different means less is also different as well. To me, this is the most succinct title and meaningful title that I have found in any scientific paper. Now he says there, the ability to reduce everything to simple fundamental laws does not imply the ability to start from those laws and reconstruct the universe. In fact, the more elementary particle physicist tells us the nature of the tells us about the nature of the fundamental laws, the less relevant they seem to have to the very real problems of rest of science, much less society. The everything else is chemistry breaks apart from the twin shoals of scale and complexity. He explains. Take water, for example. He gives this example in that paper. Take water, for example. There is nothing very complicated about a water molecule. It's just one big oxygen atom with two little hydrogen atoms stuck to it. Mickey Mouse ears. Its behavior is governed by well understood equations in atomic physics. But now put a few zillion of those molecules together in the same pot. Those zillions of molecules have collectively acquired a property that is liquidity, that none of them possesses alone. In fact, unless you know precisely where and how to look for it, there is nothing in those well understood equations of atomic physics that even hints at such a property. The liquidity is an emergent property. But what is the point? What is the relevance of my digression? Well, remember the principles of organization, order, scale, hierarchy, and emergence. Today, we will learn about specific aspects of materials in the nanoscale from renowned experts, recognized specialists. My introduction aimed at putting knowledge, my introduction aims at putting this specialist knowledge in perspective. Having done that, a generalist like me must stop here and now. Thank you.
Thank you, sir, for sharing the thoughts and necessary information and the aspects of the scale of materials in such a lucid manner. I hope the attendees will find a lot of concept to explore and discuss in depth what you have discussed in the short span of time. So thank you, sir. So may I request Honorable Vice Chancellor, sir, to kindly give his keynote speech, sir.
Okay, thank you, Dr. Taposh Ghosh. Professor Samasdar describes many aspects from different perspectives for nanotechnology. That's nice to hear. And I would like to, I can see here Dr. Or is also there, and Dr. Orijit Bagh from our university. So it's good that you have organized these programs. This is very important. And two resource persons, Professor Dilip Kumar Maiti and Professor Devashish Haldar, they'll be presenting their views on this basic, precise title is Nanomaterials, Nanotechnology for Smart Materials, something like this, isn't it?
Yes, smart nanomaterials, yes, sir.
Smart nanomaterials, okay. Once upon a time, I had some interest in nanotechnology because of the fact that I was supposed to take up certain projects and programs in the fields of chemical engineering, chemical science, and nanotechnology. And in doing that, I attained a little bit this knowledge and information. And whatever I can recollect, I'd like to share with you. Maybe many of this is not at this moment of time. Many of this has become redundant or obsolete. Still, what is there, so far I can remember, I would like to share. So basically, there is a famous Dr. Samasdar made several, presented several quotes. So I am also tempted to share certain important quotes in this nanotechnology. One of the famous quote is of Richard Feynman. This quote starts like this: I want to build a billion tiny factories, models of each other, which are manufacturing simultaneously. The principles of physics, as far as I can see, do not speak against the possibility of maneuvering things atom by atom. It is not an attempt to violate any laws. It is something in principle that can be done, but in practice, it has not been done because we are too big. That is one of the famous quote of Feynman. And all of us are quite, this right now we're convinced about the importance of nano dimension because of this fact. At nano dimension, the two different domains of science, classical mechanics and quantum mechanics, both of these are, this equally functioning. That's why many properties which are are typical features of corpuscular particles or following these classical mechanics. Here in nanomaterials, we can see there is an abnormality because they embrace certain properties associated with quantum mechanics. So this is one of the interesting thing. There are lots of these researches and understandings on this nanotechnology. And if we look into it from two different ways, from physics perspective and from chemistry perspective, two different these ways this nanotechnology progressed. Particularly, it received a boost, this research on nanotechnology, after the invention of a scanning tunneling microscope in 1981, after the discovery of Fuller in 1985. Then there was a famous book, that is Engine of Creation, written by Eric Dessler. And that created lots of stir in these scientific communities regarding this probable application and possible futuristic applications of nanotechnology. And we also know the famous, this quote of Richard Feynman: "There's plenty of room at the bottom." And that lecture he gave at 1959 that inspired this conceptual foundation of nanotechnology, because this is at this stage, this nano stage. Feynman described at this lecture, gravity would become less important, surface tension, van der Waals attraction would become more important. And this is the chronological development of nanotechnology. And then when Dessler wrote his book, very popular book in scientific community, that's Engines of Creation. And that's book, The Coming Engines of Creation, the coming era of nanotechnology. That is basically in 1986, when he wrote these books, he proposed the idea of nanoscale assembler. And he developed and popularized the concept of nanotechnology and founded the field of molecular nanotechnology. And his thesis, basically, Dessler's thesis, molecular machinery and manufacturing with application to computation, that was published in Nanosystems, Molecular Machinery Manufacturing and Computer. And that book was one of the best-selling books because it received this Association of American Publishers Award for the best computer science book in 1982. So this is one of the milestone in nanotechnology, this research and nanotechnology and popularization of nanotechnology. And then there are some experimental advances because of this. There are two phenomena: birth of cluster science and invention of scanning tunneling microscope. And in 1986, two gentlemen, Gerd Binnig and Heinrich Roher, they won the Nobel Prize, 1986 Nobel Prize in physics, because they invented the scanning tunneling microscopes. And that is also, again, another milestone in nano research. And if we look at from chemistry perspective, in colloid science, there was the concept of nanotechnology long time before. Sigmondi made a detailed study of gold salts and other nanomaterials with size less than 10 nanometers. And he used ultra microscope to visualize particles much smaller than the light wavelength. And in 1925, he won the Nobel Prize in chemistry because he was the first person to use the term nanometer explicitly for characterizing the particle size. So this is from chemical side, but there is another, this development because the famous scientist Irving Langmuir. He won the 1932 Nobel Prize in chemistry because Langmuir and Blodgett, they introduced the concept of monolayer, a layer of material, one molecular thick. And that also opened up a new, this area of research in nanofabrication. Now, another event in 1985 that is the discovery of fullerene by Eric Proto, Richard Smalley, and Robert Kahn. When they won the Nobel Prize together in 1996 in chemistry. And all this created sensation and these popularizations of regarding this nanomaterials, carbon nanotubes. That was Sumio Ijima's work. It was another important milestone in nano research. Multi-walled carbon nanotube, insoluble materials of arc-bound graphite rods in 1991. That was another famous path-breaking work, and here also that is also considered as an important milestone in the area of nano research. And then at US, there was this initiative regarding this funding of these nano projects, and President Bill Clinton, he advocated nanotechnology development because in 2000 he made a speech on California Institute of Technology. And there he emphasized the importance of nanotechnology research and this Nano Research Foundation, all these things that was created under this Clinton government at that time. And you see there were many other this counter views regarding this possible threat of nanotechnology. At the same time, people are enthusiastic about many futuristic, unimaginable applications of nanotechnology. At the same, another school of thought that emerged that there could be, this serious threat, because if nanotechnology emerge in a significant way. There's another book written by Bill Joy, Why the Future Doesn't Need Us. He was the chief scientist at Sun Microsystems in April 2000 at Wired magazine, the famous magazine Wired magazine. He wrote this book review was there. And his worry was that computer will eventually become more intelligent than we are, leading to a scenario as a robot rebellion. And because of the fact that nanotechnology genetics focused on genetics, nanotechnology, robotics, all these three technology ultimately led to devastation and destruction of human civilizations. So this another concept emerged, and many of people they also this became part of this idea. But there was our counter arguments also there, and that was criticisms of Bill Joy was also there. Ray Carnjuns, there was another article. The singularity is near. He questioned the regulations of potentially dangerous nanotechnology because in many areas, the researches on nanotechnology at that time that received a certain level of skepticism with the fact that it can lead to maybe these possible threats or hazards. But these researches went on and school and another area of research is the health hazards. And other hazards associated with nanotechnology became a part of all this research. In India, the Nano initiative started by Professor C.N.R. Rao. He was the main person, this personality to initiate this nano research in India, the Nanoscience and Technology Initiative. His endeavor basically, and that functioned from 2001 to 2006 as a part of DST initiative. And initially, it had initial budget of 100 crores, and that led to this opening up the path of taking up nanotechnology as a major area of research in many central government funded research institute and many universities. They received grants and funds from government of India and carried out research. But research, that is one thing. But right now the requirement is now how best we can translate into real product. Although there have been several applications of nanotechnology in different fields, particularly healthcare, cosmetics, and in the form of titanium dioxide, zinc. They are very popular nanoparticles used in silver nanoparticles in food packaging, in healthcare products, in clothing and disinfectants. Cerium oxide as a fuel catalyst. These are all now being used, but still there are lots of these things naturally occurring nanomaterials or synthetic nanomaterials in different proportion and compositions for ubiquitous and novel applications for different applications that needs to be these made available for the massive entrepreneurships and for translating the knowledge into economy for this for this important subjects. There are these many the blend of this nanotechnology with biotechnology that also happened in the form of evolution of subject nanobiotechnology. In microelectronics, the concept from MEMS, now it has been translated to NEMS, microelectromechanical system to nano electromechanical system. And all these things are happening. Right now, we are yet to reap all the benefits from this nanotechnology. In many areas, there have been certain, this isolated or pocket, or secluded or small scale benefits from this research and all these things. We need to have this more integrated, because nanotechnology is pervading in each and every field. Be it food technology, be it pharmaceutical technology, be it electronics, computer science, everywhere. And the famous, this law, the Moore's law, which predicts that initially when Gordon Moore, as he was at IBM, he predicted that within 10 years, this this capacity will be double, capacity of all these devices, digital will be double, or price will be half, because of this numbers of transistors that could be accommodated in this unit volume, that unit area, that would be doubled. But within 10 years, that Moore's law that was required to be revisited, because that time it was observed that 10 years is too long period. Within 2 years, that all these things are happening. Right now, the Moore's law now need to be revisited further because of this tremendous and phenomenal, this growth and applications in this particular area. And it may be like that. This with the advent of quantum computing, with the advent of all these, these high performance digital gadgets, we will get all the consumers and customers. They will get the benefit of having these devices with much higher capacity at a more affordable price in near future. There will be many these healthcare products and food products and all these things that are on the horizon. But right now we need a coordinated, a collaborated research, in such a way that from all dimension, all discipline, we can combine our knowledge, our expertise, and all these things together to make these things happen. And we have to focus on this, these natural products here, because in our country, biodiversity in terms of is this one of this unique thing, and natural resources also we are having this abundantly available. And for all these things, and we have this potential for engaging ourselves in meaningful and significant research activities. Now this potential need to be tapped. We need to have this more effective research collaborations. And I believe that within a shortest possible time, we will be seeing the emergence of a new form of economy based on this nanotechnology, biotechnology, and this taking care of all aspects, starting from environmental, healthcare, social science, electronics, and every sphere of our life. So with this, I'd like to conclude. Thank you for, again, I would like to express my sincerest thanks for organizing this very important, relevant topic, multidisciplinary interest. And I believe that it will lead to the more interest and more, this enthusiasm among all our participants. And many of them will come to know about the different fascinating features of nanotechnology. And we can have more numbers of potential researchers, and this all from all these webinars and all these things. This is our expectations. And from here, we would like to develop our knowledge community. That I say that every webinars we would like to have more, these active researchers or interested, these minds to join in fruitful discussion for having more collaboration. In this particular area for making for generating more ideas, more knowledge, and with the object of of developing a nano-based research community or nano-based knowledge community for the benefit of our learning system. Thank you all.
Thank you, sir, for such inspiring and motivational words as always. And I'm sure that it has enlightened all of our panel members, even and also the participants as well. As you mentioned from the very beginning of the nanotechnology with the famous quotes from Feynman, Drexler, and advocating the prosperity and prospects of nanomaterials, and also the skepticism for that. and also building up research groups, and hopefully we will be doing that part and building research groups for research in nanomaterials and technology with our panel members here today. They are eminent speakers in their field, in their own way, and hopefully we will build a research community definitely in participation with them, in collaboration with them. Thank you, sir. Thank you again. May I now request Dr. Arijit Bagh to kindly introduce our first speaker, Dr. Dilip Kumar Maiti, Fellow of Royal Society of Chemistry, Department of Chemistry, University of Calcutta. Dr. Bagh, please.
Thank you, Dr. Ghosh. It is a great honor to me to have an opportunity to introduce today's guest speaker, Professor Dilip Kumar Maiti, who is a distinguished fellow of Royal Society of Chemistry of London. He is in the editorial board of high-impact journals with cutting-edge researches in wide range of interdisciplinary research areas. He has proclaimed his identity in the international community. His big research group is busy with synthesis, fabrication, and designation of organic and polymer nanomaterials, device making of organic solar cells, energy storage, supercapacitor, medical sensing, and so on. He is also active researcher in catalyst designing for CH activation, ionic liquid, photocatalytic reactions, etc. His vast and in-depth knowledge are acknowledged by various national and international councils and academic bodies, which include American Chemical Society, Indian Science Congress, Indian Chemical Society, Science Advisory Board of Washington, D.C., Professor Osima Chatterjee Foundation of Kolkata, Sigma Aldrich Global Advisory Board, etc. He is the editor-in-chief of two high-impact international journals, Journal of Chemistry and Applied Biochemistry, Nanomaterial, and ChemBio Device. He is also in the editorial board of scientific reports of Nature publication, bioorganic and inorganic chemistry, material science research in India, current catalysis, etc. He delivers his service as a reviewer of different prestigious journals, starting from Journal of American Chemical Society, Nature Communication, Journal of Organic Chemistry, Chemical Communication, Green Chemistry, and so on. He was awarded his PhD in 1998 jointly from IICP and Jadavpur University, Kolkata. His thesis work was on pseudo-selective synthesis. After his PhD, he works in industries like RPG Life Sciences Limited in Mumbai and Siva India Private Limited in Navi Mumbai for a period of 2 years. Then he joined Damkal College, Basantapur as lecturer in 2000. He gathered his postdoctorate experiences from School of Medicine, Wayne State University of USA, and also he worked as a postdoctoral fellow at Department of Chemistry, Jadavpur University. In 2005, he joined University of Calcutta as a reader. He became full professor in 2009. Presently, more than 37 PhD scholars have completed their doctoral work under his guidance, and more than 33 postdoctoral researchers have worked with him. A dynamic personality like him could not be only academic. He organized numbers of international symposiums which have definitely enriched the Indian science. He organized Nobel laureate lecture by Nobel laureate Professor E.C. Nagishi in 2016, 27th January, which was witnessed by more than 500 attendees. He is rewarded by several honors and recognitions like Fellow of Royal Society of Chemistry of London, Fellow of Indian Chemical Society, Vasudev Banerjee Memorial Award by Indian Chemical Society, American Chemical Society Membership Award in 2015, Professor Sabbasati Sarkar Endowment Lecture in 2015, Professor M.K. Raut Memorial Lecture from Orissa Chemical Society, Franklin Membership by London Journal Press in 2020. With this brief introduction, I am inviting Professor Dilip Kumar Maiti Maiti to deliver his talk. Please, Professor Maiti, have your talk now.
Sir,
Thanks, Arijit.
before you start, sir, just I have a request to all the
Hello.
in the question answer box, and we will have that after the lecture session is over. Then immediately after the lecture is over, we will have your questions. Please put your question in the question answer box, please. Sir, please carry on, sir.
Yeah. Very good morning, and thanks, Arijit, for your kind introduction. May I audible? Everything is okay, right?
So yeah, audible, sir. Just can you put down your screen little bit, then you will be visible fully. I think now you are partially visible, sir. A little bit putting the screen down would be. Otherwise, everything is fine, sir.
It's okay. It's okay. Uh,
Okay,
and
please, sir.
thank you for inviting me for this talk. Mm, So, how long I can talk? Up to 12:15, right?
I think, sir, you just start and you you start your deliberation, and I think you will have 40 minutes to 45 minutes at least, sir. No problem.
45 minutes. Okay, then fine. All right. Okay. So, we work in different area as Arijit told you. So I have also a small group. They are working in different field like organic synthesis and then materials as well as their application in different capacitors as well as memory device. So these are my students who are working and my collaborator, and Dr. Tapas Ghosh also one my collaborator of my group. And also I'm thankful to the funding agencies who are giving funding, because university structure, other than funding you cannot do anything. So before I go to the my topic, so let's discuss little about the scientists. Scientists must be humble. That is actually Einstein told, and then he told that it is probably the Mary Curie who is actually uh, more not corrupted by the fame that she had won. Probably you know that she got 2 Nobel Prize, but she is very much humble to everyone. So scientists should be very humble in nature, as well as our PC Ray also told that not only humble, that should be patriotism is there, and it is usually scientists are humble, and also we do in this way that we are hunger of knowledge and we are working in that. So today I want to talk a little bit about the photochemistry, that how photochemistry is used. After that, I will go to the nanoscience as well as smart devices, how we are, what my students are doing. I will discuss that. We know photosynthesis on method where actually light is used as a reagent, and taking carbon dioxide, it transforms to carbohydrate, and the carbohydrate we light because we are taking carbohydrate as a energy source. So light, that's why it's an important topic of research. As you can see that Einstein told that a molecule absorbs a single quantum of light, is becoming excited, and they give different phenomena. And light is used for different processes. As you can see here, a lot of processes are there. Obviously, as a chemist, we will be very much interested about developing new chemistry as well as chemical dynamics. But nowadays, most important criteria is can we use solar cell for the organic nanoelectronics. So you know this electronics are really converting to the organic electronics, because organic molecule can be used as a semiconductor, and that will give you huge difference with respect to inorganic like silicon industries. So photosynthesize organic negative capacitor you can make photochemistry using carbon 19 as an ironing mechanism. So here, most important thing is photochemistry. We know that the radical is generated, and you know the radical reaction cannot be done in the reactor where the industry synthesize this molecule or pharmaceutical or anything, any chemical of that type. So you need to convert this photochemical reaction to a normal reaction, means the reaction must be ionic 19 or carbon. So photochemistry, of course, when we're going to discuss this one, first we should remember one guy, that is Sian, an Italian scientist who actually first did the photochemical reaction. He transformed quinone into quinol using light in 1886. You can see this next slide. It is very interesting to see that Sian and his colleague standing outside of his building, and there are hundreds of reagent bottles are keeping over there for the photochemical reaction, where light is used as a reagent for this particular reaction. Uh, Photochemical reaction is very interesting, and you know that pioneer scientists all over the world work in this particular area. So here in India also we have one scientist, that is Ganesh Pandey. He did a lot of work, and his student Somen Hajra, one Bengali people, he did this lot of reaction using photochemical reaction, and he has a lot of contribution in photochemistry. As you know, this photochemistry having a lot of dimension, lot of properties with time that is developed, and but we want to use photochemistry as a common mechanism. We want it should work as a carbon, nitrogen, and ionic mechanism, and we can use photochemistry as a photochemical reaction or photochemical excitation of different type of device we want to use, because light is cheap and easily available that we can use for different cases. So these are the basically catalysts, organic catalysts, we can be excited in present light, and you can use this one as a catalyst for a particular reaction. My group is working with hypervalent iodine for a long time when I started research over here in Calcutta University. And we observed that hypervalent iodine can be influenced to ionic reaction or radical reaction. Whenever we can use a different ambience, it can transform to this one. So out of that idea, we have started thinking that is it possible to make uh, radical reaction to the forming of nitrine, and this nitrine can be performed, so that this reaction can be useful in the industry to synthesize different type of molecules or chemicals and pharmaceuticals. So it is possible theoretically that okay, it can transform to carbene, it can transform to nitrine, and nitrine can be used for synthesizing as a diaziridine, this type of compound which is very unstable, but it is possible to synthesize this one. Okay, so we started this reaction. You can watch over here a amine and want to diol when excited with light, and this light actually activate this one, and it can transform to diaziridine, which is a very unstable compound which even can be synthesized under mild condition. As you can see the only solvent is there, and room temperature reaction is organized, and in presence of triple bond it transforms to corresponding heterocycle or 3 plus 2 cyclohexane. And you can see this reaction can be done 1 to diol, and this will nitrine, and in this medium that the imine will form, and that cyclization takes place, it will give you this diaziridine compound. And that is the first observation using nitrine, and this is uh, published in Organic Letters, and it became actually ACS editor choice in 2017. And you can see that different type of molecules can be synthesized. Not only that, this amine having chiral center that will be preserved during this reaction, and it will give you the different product which is chiral in nature. So it is basically asymmetric synthesis. And you can see we can put different group at the CH2 group, where it can exist and can give you different type of compound. But if you can see that whether it is radical reaction or not, if it is a radical reaction, so there will be a deuterium exchange. You can see over here, we studied this reaction, there is no compound we found where deuterium is exchanged. It is hydrogen is there. When deuterium is there, it is observed that deuterium is incorporated in the preserved in this particular methylene group. So this indicates this reaction is not a radical reaction. It is basically passing through nitrine intermediate. As you can see, we watch this reaction. It is very simple. Amine will reacted with PHI. So it will be imine type of bond will form, and when you have the diol, that is also performed this type of cyclic intermediate with hypervalent iodine. And that on excited rose bengal is the photocatalyst that excited over there, and that can transform this double bond I to PHI and nitrene, as well as break down this carbon-carbon bond to nitrene, and this is imine, and this nitrene and imine will cycloaddition product give you the diazoline. So that's very interesting to see that radical reaction is not the idea that when photochemical reaction, radical reaction is going on, we can transform to different type of method. And this is again another reaction we studied very recently. Just last year we published this one, but before that, you see that we studied a reaction how triple bond can be transformed to corresponding keto ester and amide. You know the amide synthesis always we need anhydrous condition, but we use water as a reagent for this amidation reaction. So we thought, is it possible to perform a transformation where dual catalysis will take place and the radical reaction will go on, but the radical concentration remains same throughout the reaction, and ionic mechanism will be transformed this corresponding product to this one. So this is the cycle you can see where this ionic reaction is going on, and this is the cycle where actually it is non-radical radical mechanism is going on performing that particular reaction. So this is the reaction. It's very simple. You have 1,3-diketone, you have a amine, so it will give you the ketoamide. Again, it is a very unstable compound. It is at room temperature. You are getting this particular compound. As you can see, that different type of compound is synthesized with the heterocycle, electron withdrawing, electron donating, all type of reaction actually possible using this particular reaction. And also not only that, you can install chiral center in a particular compound, so perform asymmetric synthesis. Not only that, another interesting part is oxalamide synthesis, which is very unsymmetrical, is very difficult job. So we also shown this particular reaction. Here also the same thing, that oxygen is coming from hypervalent iodine. As you can see, this hypervalent iodine having O18 that is incorporated in particular product. And also we studied this reaction when the carbonyl having more carbonyl character, that bond, carbon-carbon bond actually broken down to give you the particular bond. Okay, so this is the cyclic pathway. This is radical pathway over here, and this is the ionic mechanism. So ionic mechanism you can see, this is the copper catalyzed reaction and transform this one, but the radical reaction basically here this photocatalyst actually using Y transform this one, and it is reduced to corresponding UI, and this is the way it is going on. So this work also very excited result we found, and it is published in Chemical Communication as a hot paper in last year 2019. And this reaction can easily transform to understand that whether this can be done using, so this can be done using proper concentration, and we studied in quenching mechanism that also established that this reaction is passing through ionic mechanism, not the radical reaction. Okay, so my students are also doing different type of reactions. You can see another photochemical reaction can be done in different ways. That time is less, so I'm skipping this one. We study CH activation reaction. Is very interesting. It is published in this running letters, and you can see different type of sp3 CH activation is very difficult to get, and we studied very simple way to get this product. Not only that, olefination of the particular this hydrogen is transformed to this one, olefination can take place, as well as alkylation will take place, and that is published in this year. And another one is very interesting to see that a triple bond with amide bond can transform to 5-member cyclization, 6-member cyclization, as well as 7-member cyclization can be done. And also benzene-mediated reaction can be done with different type of reaction. So with these few things, so I'll skip organic synthesis. So most of the there are I came to know that there are students from graduate as well as postgraduate students are there. So let me introduce a few slides dedicated to what is nanoscience so that you can understand. Then we will go for this organic electronics, organic nanomaterials and devices. how basically we are using organic compounds. We are synthesizing so much beautiful compounds, and how can we are using these molecules for different purposes. And it can easily can be done, transformed to corresponding organic nanomaterials, and can be transformed to sensors, can transfer to devices, it can be transformed to different type of what you call reagent also. So nanoscience basically it is a Greek word. Nanos means it's a Greek word, come from means dwarf means small. It is actually 1 billionth of a meter, but it is very interesting area where chemist, physics, material science, engineer, every people, every streams are working together to do something great for the human beings. So you can see the nanoscience. Just it is we know that Feynman is the father of nanoscience. He told actually in 1956, 59, he told that there is a plenty of room in the bottom, and you can write 5 volumes of Britannica at the top of at the tip of a pin. So you can understand in a pin in tip of a pin very little area. There you can write 5 volumes of dictionary. It is possible. Then everyone asked, "Is it a joke?" Then he told, "No, it is not a joke. It is possible. You can write, but you cannot see. If you want to see, then you need to improve the microscope 100 times better, whatever the resolution was there in during 1959." And with that inspiration, actually, several microscope is developed like ACM, TM, ATM, XM, and so many others, and this is they got Nobel Prize. And during this one, this is you can see in 1773, William Brownlee wrote a letter to Benjamin Franklin, and he saw this is the observation. If he's told that if you put a drop of half a spoon of oil on the pond, and it remains, goes surface almost half a acre. But interesting thing, it looks like a glass. But what happens actually, this is oil is not miscible in water. So it remains on the surface, but it is spread out unless it makes the nanoparticle. So this is basically oil with nanoparticle. That's why color developed, and it's shown it's not just transparent, but it is actually yellow in color. That is actually the size of a nanoparticle. Let's see how can you think that dimension of a nanoparticle. We know that smallest thing we watch, that is our hair, and this is the hair part of the hair. But another thing you have observed, that is red blood cell. During class 12 microscope or BSc standard, we observe that red blood cell, how it looks like. So this is the width of the hair, and this is a red blood cell. Even red blood cell, if you see, the dimension of a red blood cell, that is also 6,000 nanometer. Means it is not in the nanometer scale. But when you go to the DNA and RNA, it is actually in the nanoscale. It is dimension. This width is actually around 3 nanometer. Although it is DNA, RNA, and protein molecule, they are in the nano range, and they are basically width are very around 3 nanometer, and that's why these are nanoparticles. Maybe that's these nanoparticles are there here in our body. They are doing so many biochemical transformation very easily at the room temperature, and performing great job for us, and that's why we are living. Okay, so you watch, this is a simple microscope over here, that this is the particle and this is the electron beam coming over here. And this is the principle that in microscope, that the different type of microscope arise. As I told you, that how can you define a nanomaterial? Nanomaterial basically, if a dimension is 1 to 100 nanometer in any dimension, means length, width, height, any dimension, or any two dimension, that is 1 to 100 nanometer, then we call it a nano-dimensional material. Okay, so you watch this cartoon, it is very interesting to see. When you shoot a particle, what you need a gun. But this guy want to shoot a nanoparticle, and he took a microscope, and then only see. So that is the very good definition of nanoparticle. Nanoparticle is so small you cannot see with your naked eye, but it has a lot of new properties. So that's why he took this gun to watch this nanoparticle and then shooting with a gun. Okay, see this nanoparticle. You know gold is having golden color. So this is the color of a gold. So it is golden color. And if you go to the atomic stage, gold having no color. But when you have a cluster around 1 nanometer size, it is orange. But interesting thing is it is non-metallic. So one one conductor become insulator when its size become very small. When it is come to 3 to 30 nanometer, it become metallic, it become red, but it become metallic. So that is very interesting. But what happened in between them, 3 to 30 nanometer means in between them, is basically in one stage it will come as a semiconductor. So you can see over here, same gold we can make as a non-conductor, we can make as a conductor, and we can make a semiconductor, just changing the size. And you can see different type of color. So this is a micron size, we call it classical physics, but at angstrom size we can call it particle of angstrom size, we call quantum mechanics. But at the nanometer scale, fundamental property that depends on exactly how big the particle is. Not only just size, but shape is also important for a particular particle to be nanoparticle to give you the property. Now the question is, where are the properties? You can see over here nano gold having different color when they are in the solution, having different size. And you know this particle having, when they are small, their basically packing is very good, and that's why they are actually very good for conductor, and they are very good for heat transfer. That's why nanoparticle is our choice for a different type of research to giving different properties for the beneficiary of human. What are the new properties? In optical properties, electrical properties, magnetic properties, physical properties, and chemical properties. So there is no other properties over there. All properties can be changed when you go to the nano dimension, and every property will change. As you can see, it's a very simple example. If you have a bamboo, you have elephant and guinea pig. Who will be very comfortable when sitting on it? Obviously, guinea pig is very easy to sit for this one, but for elephant, it is very difficult. So that's why bigger one is not better, always smaller one is better. The smaller thing gives you new innovative properties. Okay, let's come to the organic electronics. So today I'll discuss a little bit about organic electronics so that you can understand how organic molecule can be used as a semiconductor, and even insulator, it can be used as a conductor. So if you go to the solar cell, you know solar cell, this sunlight is coming over here, and there is silicon, and this photon will come and eject electron from silicon. In the opposite side, there will be hole, and in the middle there is a glass electrode. So hole will be generated. So there will be a voltage difference between them. So you can go for lighting, and you can go for charging batteries. You can use in the night time, so for the light or other purposes. Now, then one photon can eject one electron from a silicon, and it is observed only 46% of the incident photon is effective to produce current in case of silicon. Very interestingly, when this silicon is removed, pentacene, 5 benzene ring is fused together. Pentacene is used, it is observed that current, whatever we are getting, that is 43% more sensitive than the theoretical value. That means when you 100 photon, incident photon is there, we will getting 100 electron in case of silicon. But when you have the photon, 100 photon, you have the different material like pentacene, then you will find out 143 electron is ejected. Now the question is, how it is happening? The reason is very simple. As you know that organic molecule having pi electron, these pi electron are actually loosely bound. They are on the surface of this material. Actually, this pentacene makes a nanomaterial, and the surface electron can be ejected easily because it is loosely bound, and that's why it happens. And that is the reason that one photon ejecting two electrons. So this is very interesting phenomena. That's why organic compound is very important. So pentacene, one photon is ejecting two electrons out of it and give you this particular current, and that's why it is 143% effective with respect to silicon. Okay. Now, if we go to the organic nanomaterials, so it is basically, if you see the building, organic molecule having very larger size. So you can think that is a brick, like one molecule having a one brick. So they can arrange into different array. They can arrange in the face to face, or it can be arranged head to tail. So face to face is called H aggregation, and J aggregation is head to tail arrangement. And what is the property of this one? That H aggregation occurs when it is observed that when UV, we put in UV light, and you will see that hypsochromic shift will occur. Means that light, uh, UV light, you will see the absorption at the shorter wavelength. But when you have the J aggregate, this material, you will see that bathochromic shift. That means it is appearing in longer wavelength. So this is a J aggregate. Not only that, these organic compounds can be used a p-type and n-type semiconductor. That is, if you know that when organic molecule is formed, there is a HOMO, there is a LUMO. HOMO is called highest occupied molecular orbital. LUMO is called lowest unoccupied molecular orbital. And when HOMO is at the lower and LUMO is at higher, and when HOMO having energy high, it can easily release electron, so it can create a hole. So any organic material, when that HOMO having higher energy, you can use this compound as a p-type semiconductor. But in case of organic molecules which are having lower LUMO, that means you can eject electron. So this compound can be used as a n-type semiconductor. So this is the simple explanation where you can use organic molecule as a p-type as well as n-type semiconductor, because you want to make a device, you need this organic molecule this way. But most interesting part there of this one, that as the organic molecule having so many properties, then why people are not using? People are not using because of lack of knowledge. The reason is it is very difficult to make them nanomaterial. So that is why that is called aggregation. As you can see that if you need to arrange this one to head to tail, if one molecule go out of this particular array, then this basically whole flow or electron flow or heat flow, everything will cut off, and this material is ineffective. So that's why aggregation or fabrication of material is a very important task. As you can see that always people think that polymer is good for making nanomaterial, but we had shown my students make different type of organic nanomaterials using small molecule. As you can see, this is looks like a cauliflower. This is like nanofiber, and that is like it is called nano belt, and so nano seeds. So different type of compound you can make using different very simple organic compound can be this one, but you need to install different type of weak interaction. That all molecule cannot be used as a organic materials you want to use. Now, what is that? You can watch this is a molecule. This is a very simple molecule. It looks like it doesn't have that much unique criteria, but it makes this material over here. And this is when we go for engineering, crystal engineering, we found there is a strong hydrogen bonding even with oxygen with the hydrogen which is triple bonded CH. Not only that, there is also CH having over here having aromatic ring, it has a hydrogen bonding dipole interaction. So this is the way actually all those molecules they are arranged very nicely. As you can see, these aromatic ring are packed just one by one by one by one like that, and that indicate this type of network present in this nanomaterial, and that indicate that this molecule can be used as an organic nanomaterial. So what are those weak interaction? Those weak interaction like hydrogen bonding, ionic interaction, sometimes dipoles interaction, dipole-dipole interaction, ion-dipole interaction, hydrophobic interaction, Van der Waals force of interaction. So this type of interaction actually playing as a gluing interaction. We call it gluing. So it's to stick one molecule with another molecule to give you this particular nanomaterial. So there are several molecules can be arranged in this way to give you the nanomaterial. Let me tell you one sensor. So how we develop a sensor using nanomaterial. So that's why these are called functional material. We have synthesized a receptor in a simple organic synthesis sequence. Over you can see over here, this is oxygen, this is OH. And you know phosgene is a very poisonous gas. It can, people can be die just inhaling this one, but phosgene, very interesting part is it is a we can say that it doesn't have any sense. It doesn't have any smell also. So this smellless gas is very poisonous, and it can kill human if you expose to phosgene for a long time. So it can be done. So, but trace of phosgene, you need to activate this one. So we use this molecule as a nanomaterial, organic nanomaterial. And the nanomaterial surface is highly polarized, and reactivity of this molecule also increased. And easily it can be converted to corresponding oxazole molecule. Over here, you can see that cyclization takes place, and as a result, that ESIPT, which called excited state intermolecular proton transfer takes place, and as a result we got this particular parameter. As you can see, this is the compound which is a nanomaterial form over here. This is a ACN image of this particular compound which is a nanomaterial, and you can see this material actually given on a paper streak or a aluminium streak like that, and it is kept in a different boxes having phosgene concentration different. As you can see, with immediately it will transform to a different color, and this color intensity is showing how strong the phosgene is in that particular region. And this material is whether it is selective, yes, it is selective. You can watch only phosgene is sensed, but other things are very little or very negligible. So this is very selective, and this paper is published in Journal Medical Chemistry A. And, it is last year it is published, and published by Devasis and Mike. Okay, so another interesting part we did, that is a dipeptide fused with diphenhydramine, and this is called halogen bonding. So this halogen bonding, this paper is published this year, but it is a very good luminescent material. This is a very good luminescent material. As you can see, it capture cyanide to give you different colors. Cyanide, you know, cyanide is another reagent, another what you call smellless compound, which is very poisonous, and if we take this one, we can die. And usually that water may contain this one, that thing also is very urgent. So cyanide, that's why you can detect very easily. As you can see, this colorless compound transform to orange red color very easily, just transform to this one using cyanide. And this is a very small molecular again. You can see this is a dipeptide, and this is the nanomaterial. You can see over here all this nanofiber. This is a 5 nanofibril basically. As you can see that it can give you the light emitting gel. It can transform to this one. If you use light, it can transform to gel. It performs aggregation induced emission platform, and it give you different color. Not only that, it can sense solvent, it can sense water. So it has a multi-dimensional application of this molecule, which is very simple, small, it's very easy to synthesize. But how you are getting this one, that is basically aggregation is done by halogen bonding. You know hydrogen bonding, maybe oxygen and hydrogen, you have a strong electronegative and electropositive hydrogen, and so it has a bonding, strong interaction between them. They have a delta plus, delta minus. But halogen bonding can be done using halogen or halogen oxygen like that, and that bond is also very important, and that we focused over there, which is published just a few months back in ACS Applied Nanomaterials. And this work is done by Tanmay and Sumon is very good areas. Okay, so another interesting part is, let's see that very small molecule we have synthesized, and we observe that DMSO during crystallization it gives different color, and this is used as a inkless writing. So you know that if you want to write something, you need a ink and you need a pen. But here we are telling you don't need any ink. You just need a pen having hot tip that you can write over there. Let's see that what is happening. So this is the molecule. This molecule having very simple. You have a double bond. You have also in this molecule, and you have a interaction pi stacking as well as oxygen interaction, and they have a different arrangement with DMSO. But what happens if it is heated little bit in sunlight, or if you just heat to 50-degree temperature, and immediately that DMSO is removed and it transforms to corresponding stack of that particular compound having no DMSO, that obviously that color changes. So you can see that material with DMSO having green color, and this is basically a luminescent color. But when transformed to this one, it is basically orange type of color to this one. Okay, let's see that how can you make. So you can see in the next slide, maybe over here, you can watch this. So this is so inkless writing, and not only that, this is the page, inkless writing in a page where you don't need any cellulose. You have a plastic sheet, very simple. You watch this one. This is the compound we used, and this is your utensil, and this is the paper having this organic compound. Now you put this stencil over it, it looks like this one. So there is a gap ABCD like that, EFGH, and you put this sunlight exposed to light, then you remove this particular stencil, then you will see it is already written in your page. So this is very interesting, and you want to remove this one, you just erase this one. So you just make it little heat, so that will transform to corresponding uh, brown color strip where the DMSO is completely removed. So you now you have want to make it again go back to your new page, just expose to DMSO, then new page is ready for the writing. Now you can reuse. So that means cellulose, the paper we don't need. We need only compound few milligram in a plastic sheet. You can reuse in this particular way, and also you can rewrite it this one. But not only that, we need to expose sunlight. Very simple way. You make a pen, and that pen will be attached to a battery, small battery, and when you switch on your pen, that tip of the pen become hot. That is the temperature around 50-degree to 80-degree like that. Now you don't need sunlight. You can write with your pen on that paper whatever you want to write. If you want to remove this one, then you just hit this one, then it will be removed very easily. You can see this is the page. This is you are writing with a pen. Now it is written. Now you suppose thought that we don't want. We want to go back to a particular page. I want to refresh this page again. So you make it hard. It will be this page, and again you expose to DMSO. Your paper is ready for writing, rewriting. And this is called inkless writing. So you don't need ink, you need hot pen that you can write over there, and you don't need to, if you want to rewrite, you just make it heat and expose to DMSO, your paper is ready. So you don't need to throw it away. All this paper we usually throw it away, so you don't need to throw it away in this way. But most interesting thing is this material can be used as a security material. So what is that? Suppose one deed is made, and that the deed, in that deed written in the court, and suppose two people, promoter, they are thinking that they made this particular building and they are claiming for that one. So High Court judge told them that, okay, you bring the proof within 30 days, and if you don't 30 days, and if you can prove, then deed is yours, and if it is not, then we can destroy this one. So if you want to destroy, there is a problem, security problem, that paper may go to somewhere else, and then it can reach to a particular guy, a promoter, and it can create problem. So what they can do, they put this chamber, all this deep keeping the chamber, and the chamber is automated chamber. After 30 days, if it is not solved, then that automatically heat will be generated, and that paper will be transformed to again this yellow paper. There will be nothing written over there. So this is, that's why this is called that security writing, security material. So one simple compound can be synthesized. It can be used as a paper. It can be used with the inkless writing. It can be also used as a security material. Okay, let's go for a device. So we are very close. So we make a device. Now, I just give you one sensor, example of a sensor. Once I told you that just previous one that you can make a security material means functional material. Let's give you one example that how we are making devices. This is a phenazine molecule. This is a pyrene system, and it is close to this nitrogen, and this is a long chain hydrocarbon. And they make a stack over there, and you can see this is make a nanomaterial. It's a nanofibrils that is made by this material. So this can be transformed to corresponding device like this, and which is that width is maybe 100 nanometer thickness. It is just a plastic sheet, but it is a very good device, which is a memory device. Okay, you watch over here how we made this one. So you can see this is the ITO. So this is the gold, this is the electrode, and this is the blue one is the material, organic material coated, being spin coated, and again we put this gold as a layer over here, and now it is connected, and now it transformed to corresponding device. Device is looks like this one, which is very thin and it's very light but more sensitive. Now let's see what is that. Now if you watch this one, we call it RAM, resistive random access memory. And you watch over here that when you have a zero voltage, if you decrease the zero voltage to go to the -15, it goes over like this and it will jump over here. So it can write this material. Now you increase, again it is going and coming to zero, and you increase to positive, it will go up. Again it goes to +1.5, then immediately it will come down, and then again it will come to the zero. So this type of material is called RAM, resistive and random access memory. Nowadays we are using computer who is having RAM, random access memory, but the new development is coming that is called resistive random access memory. But we developed in a different dimension. We are calling it ORRAM, means organic resistive random access memory. And this ORRAM is very good for computer, which can be used as a what is called device for the memory device. And not only that, it will not create any heat because you need very little current, and this is also milliampere range. So it will not create engine. You know probably that for keeping computer cluster, you need a cold chamber, and then also you can start this using this type of computer. And when this RAM or ORRAM will come, that you don't need this one. Not only that, this chip will be very small, so you need only the screen of the computer, that is sufficient for a computer. You don't need a separate space for the CPU. Okay, you see that how we added the value for this particular device. When this type of material is phenazine is mixed with stearic acid, and stearic acid having more amount, maybe 75% stearic acid, 25% phenazine molecule. And you interestingly you observe, you watch over here like this. Here we go to the negative, it goes to -1.5 volt, and it is jump over here. Now you increase the volt, it is coming to 0, but then you increase, it goes to +1.5. But in this material, it will not coming back to the 0, but rather than it is going back in this way. What does it mean? It means this material have a different property. Means you can write, you can read, but you cannot erase. So that's why this is called write once, read many. So that means that hacking is going on. There are a lot of things that website of a particular people can be removed and can be reformed and can be modified, but it is not, you cannot modify this one because it is a write once, read many type of memory, and it is very important use in case of voting machine. So once you write, you cannot rewrite. So there is no change. The magnetic field cannot change this one, and not only that, it is an organic material, so there is no magnetic moment. So there is no question of magnetic field. What is happening nowadays in the, you know that there is a fight between Didi and Modi, that there is obviously this that there is a change of ballot box, means your machine that can be done using very easily by magnetic field. But this organic material It is not influenced by any organic materials. You can use write once and read many times. So once you wrote, you cannot remove and you cannot do anything with that particular device. You watch this mechanism, that how it is working. This is the phenazine molecule. You can watch over there. This is the keto group, which is electron withdrawing. So it is pulling electron towards itself. And that is the reason that if you go back, that once this is voltage is increasing, you can see it is having resistance. And after some time it cannot, and then it is obviously shoot over here. And you can watch over here. So it is electron withdrawing. So it is a resistant. So electron flow is stopped. But after some time, when this voltage goes up at minus 1.5 so millivolt, you can see that amide bond can be tautomerized. So now you can see this is the molecule having a double bond conjugation. So it push electron towards itself. Now it is a conductor, and that is the reason that is sharply increased over here, here to here, and here to here, and that is the reason that it is transformed. So that's why the resistance state is called off state, and this communicative things or this conducting stage is called on stage. Now, if you want to keep on stage strong, then how can it be done? That is the role of stearic acid over here. You watch over here, you have a double bond N, is stearic acid having OH, so it has a hydrogen bonding with tautomeric OH over here. So stearic acid, so it is called stabilized on state. So as stabilized on state is there, this is the reason that it is going but not coming back to the zero level like RAM, but otherwise it is going back the same way. So that's why you cannot rewrite in this particular material. So there are several applications, but electron voting is the very good application. So you can watch, we wanted to make RAM, but out of that RAM we got, but we have got the new observation, which is called WORM, which is right ones with many type of properties. Okay, so thank you very much for your presence hearing. I am in the nature group also. You can submit papers over there into like this one. And thank you very much for your spaces. And thank you very much. Tapos?
Yes, sir. Yes, sir. Thank you, sir.
Sir, hello.
Yes. Go. Yeah. Thank you, sir. For sir, is it audible now?
Dr.
Your
Ghosh, your
voice very.
voice is not coming, please.
Is it audible now, sir?
Yes, it is better, but try to get a little closer even if you can, please.
Yes, sir. So I hope right now it is okay.
Yes, it is better now. It is better now.
Yeah. So let me thank Dr. Maiti, and thank you, sir, for taking your time and giving us consent to be here with the webinar as a speaker. And it was a mesmerizing session for last 40 minutes or so, and you have finished very within your time schedule. And thank you for capturing everyone's complete attention. And your talk was so much informative and elaborative. Especially, I guess the students get a very good flavor of the nanomaterials and the device applications, along with the organic synthesis part that you begin with. So it will be very helpful them, and it was a pleasure to listen such stimulating and fascinating presentation from your end. And on the topic of the synthesis nanomaterials and its device applications. And I think it undoubtedly all the participants, be it the students or the researcher or faculties or the practitioners of chemistry at the interface of material science and chemistry, will take information from there, and they will use that in their individual fields of expertise. Thank you very much, sir. And
Thank you.
yeah, so in the question answer box so far, we have one question that what is the future of this applied chemistry version after the MSc course? I hope it is from a student point of view. They have asked that. So, sir, could
Yeah.
you take the question? Yeah.
Yeah, this is actually a good question. In my talk that you have observed that we synthesize different molecule. Now, what is the use of different molecule in chemical sciences? That is the nanomaterial. And you have seen that one organic compound can be used as a write once with many type of application. So this is a device where you can use as a memory of a particular computer or chips. You can also use as a RAM. That RAM will be not heat generating, and it is less current consuming. It is smaller, and the memory is almost 10 to the power 5 times greater than the normal memory of a computer what we are using right now. So in case of this memory device, that is very interesting. And you can see another one. You can use the organic compound as a what you call inkless writing. You can use as inkless writing. Not only that, you can use this one as a security material. And you have seen the another application that poisonous gas can be sensed very easily, and you can use at home so that you can understand that phosgene is there, because phosgene is what is called smellless gas. So you cannot understand you are exposing this phosgene, which is lethal, and people can die on exposing to this one. So all of our three molecules, we have, I showed you the three different type of application, and I had shown that how you can use light as a reagent for a particular reaction and to transform organic synthesis. Taposh?
Yeah, thank you, sir, for answering the question. And if any other participant do think of questioning anything else, you can also put it in the question answer box. And after the end of the final sessions, we can take the questions. And I hope the sir will available for us till that.
Okay.
And
Okay.
thank you, sir, for the present moment.
Please that
Thank
time
you,
make a
sir.
call.
Sure, sir. Sure, I will.
I'll be in
Sure,
meeting,
sir.
so I can continue. Okay. All right.
Sure, sir. Sure, sir.
Okay.
Thank you, sir.
Thank you.
Thank you.
Thank you.
Thank you,
Thank you,
sir.
sir.
So, yeah. So, may I now request Dr. Bag to move forward and for our next session with our next eminent speaker, Dr. Debashish Haldar from Department of Chemical Sciences, ISAR, Kolkata. Dr. Bag, please introduce our speaker.
Thank you, Dr. Ghosh. So we are very fortunate. We have two eminent speakers today for our webinar, and we have already witnessed a very excellent talk by Professor Dilip Maiti. And now we are going to hear a similar kind of enthusiastic talk from Professor Devashish Haldar. We are extremely delighted and fortunate to have such a professor with us, who is a distinguished professor of chemistry in our country and Sir Alexander von Humboldt Fellow. Professor Haldar completed his graduation in chemistry from the University of Calcutta in 1997 and completed his MSc in chemistry from the same university in 1999. Then he moved to the Indian Association for the Cultivation of Science for his doctoral work. He was awarded his PhD in 2005. After his PhD, he gathered vast experience during his postdoctoral research with different research groups in different countries. He moved to Bordeaux of France as postdoctoral research associate in 2005. Then he joined a Leverhulme Trust postdoctoral fellow at the School of Chemical Engineering and Analytical Science at the University of Manchester of United Kingdom in 2006. He was also a postdoctoral research fellow at the University of Würzburg of Germany for a period of 1 year from 2007 to 2008, where he worked with Professor Kasten Smook as a Humboldt Fellow. In 2008, he returned back to India and joined to the Department of Chemical Science, ISAR Kolkata, as an assistant professor. He became a full professor in 2018. His research work includes developments of smart peptide nanostructured materials, synthesis of amino acid analogues with tunable functionality, self-aggregation and self-aggregating system from pharmaceutical small molecules as delivery vehicle and sustained release, low molecular weight gelator compounds from receptor substrate complex, polymer peptide conjugate as ECM for tissue engineering and wound healing, artificial light harvesting system, and designer ion channels and catalysts. His work is recognized by several national and international academic bodies. In the year 2016, he got the Young Talents Award from Crystal Engineering and Communication and Emerging Investigator Award from Journal of Material Chemistry A, which are two reputed RSC journals. He also got the Outstanding Faculty Award from Venus International Foundation of Chennai, India, in the same year. He was also a recipient of the Japan Society for the Promotion of Science, commonly known as JSPS Fellowship, in 2006. So far, he has guided more than 12 PhD scholars. Presently, more than 6 scholars are pursuing their doctoral works. There are also postdoctoral researchers and MS project students. Professor Haldar has published more than 120 research articles in various prestigious international journals. His H index is 24 and I-10 index is 48. With this brief introduction, I welcome Professor Haldar to deliver his talk. Please welcome, sir.
Thank you, Abhijit. Abhijit, thank you. So am I audible?
Yes, sir.
Yes, sir, you are audible, sir. So please
Okay.
share your screen, sir. Yeah.
So, good afternoon, and I welcome you all to my today's presentation entitled Peptidic Smart Material, Opportunities and Challenges. So first I thank Taposh and Makaut, our next door neighbor, for organizing this nice webinar. And also this is almost lunch time. I will not take much more time. So please be with me for some time. Okay. And for the students who have not explored yet the ISA Kolkata campus, so we are next door neighbor to your Makaut, and we have very nice campus. So I invite the students to come and visit our campus. Okay, so now I remove almost all the introduction part as it is going to be late. So directly I am entering in my research area. So what exactly we are doing in ISA Kolkata Department of Chemical Sciences. So we are developing designer synthetic amino acids and analogs. So all of you know that amino acids are very important part of our life. It's lots of things are happening inside our body with the help of amino acid each and every moment. And there are 20 coded amino acids, lots of natural amino acids are there also, but still we are looking for particular amino acid with our own design. And till date, we have developed many amino acids. It's more than 25 amino acids we have developed in our lab with particular fashion. So there are amine group, acid group, as well as there are chromophoric systems. So we can use that amino acid for our own purpose. We can study that amino acid inside the system, inside biological material. We can study their biochemistry and all this one. And here we have shown the examples of few amino acids that are completely crystal structure. So we confirm that we have made that amino acid. The synthesis is really tricky and there are lots of things to do. but we can scale up in gram scale. So if anyone is interested about this amino acid, want to do something with our designer amino acid, we will be happy to provide that. And then we are doing what we are doing with that amino acid. So we are doing many projects, like we are mimicking the protein structure and function. And then we are making nanostructure material. We are using that nanostructure material as delivery vehicles by wrapping the drugs or some important materials, and then using them for sustained release. We are using our peptide or peptide mimetic as a stimuli responsive gels. So they are the gelator material, or we can use them as a synthetic receptor and conducting material for light harvesting system, and also porous organic material and channels for passing something, and then amyloidogenesis and its inhibition studies. So that's the overall project that we are taking care of in our lab. But one thing we believe, that a very minor chemical change has major impact on the total property of a chemical system. And for example, say this is a compound that we have made from meta-aminobenzoic acid, a very simple compound, meta-aminobenzoic acid. And then we have protected that meta-aminobenzoic acid. One side is butoxycarbonyl, and commonly known as BOF, and another side it is the ANN dicyclohexyl urea. So what happened? The compound now it's formed a duplex structure through intermolecular hydrogen bonding interaction. We have studied the structure of the molecule, its interaction by all the solution phase studies. And now this duplex structure is very stable. So what we have done next, we have replaced one proton by bromine. And what we found, that now the compound is phosphorescence. So phosphorescence is a property generally found in metal complexes. But here we have purely organic compound, but still this is phosphorescence. So what makes the compound phosphorescence is that halogen bond. So just last lecture, Professor Maiti was talking about halogen bond. So here we have employed the same halogen bond, the halogen bond between carbonyl and bromine, and that helps to make the molecule phosphorescence. And we have studied all these phosphorescence properties with microscopic as well as spectroscopic techniques. And we thought, so due to the heavy atom effect of bromine, our non-phosphorescence molecule converted to a phosphorescence molecule. So what happened if we incorporate a heavier atom in the system? So we just replace that bromine with an iodine here. And now we found that it's the phosphorescence gone. So the change from hydrogen to bromine, phosphorescence appear. From bromine to iodine, the phosphorescence gone, because there is no more halogen bond. And we have published this in Chemical Communications. And then we have extended this study with a longer foldamer, with a longer oligomer, and by incorporating 2 meta-amino-benzoic acid moiety. And we have studied by all these spectroscopic techniques using NMR, 2D NMR, and all this. And what we conclude, that now with the longer oligomer, it's actually forming a duplex. Not only a duplex, it is forming a double helical structure. So like the DNA double helical structure. And so this is the crystal structure. So we confirm that from the crystal structure. So this is the crystal structure of the shorter oligomer that contain only 1 meta-aminobenzoic acid. And here it is forming a duplex. But when we are going for the longer oligomer that contain 2 meta-aminobenzoic acid, and now it is forming a double helical structure that's stabilized by intermolecular hydrogen bonds between amide functionalities and the pi-pi stacking interaction between the aromatic functionalities. And so we can prepare a double helical structure using simple organic molecule, and that is very stable, and we have published this in a chemical communication paper. And the interesting thing is that now if we change the environment, so previous double helix we have made from chloroform, we have studied in dichloromethane, but now we change the environment from chloroform or dichloromethane to acetonitrile or methanol. What we have seen that instead of a double helix, now it is forming a supramolecular sheet-like structure. So with incorporation of a solvent, by changing the polarity of the solvent, we can convert a helical structure, supramolecular double helical structure, to a supramolecular sheet-like structure. Well, and then we have introduced a very nice peptidomimetic compound. And from the heading, you can understand that we are trying to mimic a spider silk and spider web. So what we have done, so this part, this is a diacid, and we are familiar with this. So we have taken chemistry in +2 level, we know that this is a diacid. And with this diacid, in both sides, we have incorporated amino acids. So which kind of amino acids? Tyrosine and lysine. So we have made 3 compounds. So with one compound, it is both side tyrosine. With one compound, it is both side lysine. And with one compound, it is both side. Sorry. So there was a power cut. I think it is now okay. So with one compound, we have one side leucine and one side tyrosine. And now what happened when the compound contain tyrosine both sides, the compound is liquid. When the compound contain leucine in both sides, the compound is solid. We have the crystal structure. And when it is one side tyrosine and one side leucine, the compound is liquid above 20 degrees centigrade, and it's a semi-solid below 20 degrees centigrade. So you have the experience in winter early morning. If you go to garden, you will see a lot of spider web that you can see that. And once the sun rises, the temperature increases by about 8 or 10 am. Again, if you go to garden, you that is, but when the temperature increases, so it vanishes. So we have made the same kind of thing. So what we have done, we have used a spatula or a needle to prepare a spider web from that material under 20 degrees centigrade. So in this panel, this is the web that we have made ourselves using a needle. And this is the actual natural spider silk, and that is on my window panel. And we have tested using optical microscope, and we found that the property of our synthesized compound and property of natural spider webs are same. At least the optical properties are same. And then we have studied with rheology, with microscopy, like the scanning electron microscopy. And we found that actually the material is made of fibers, and that fibers make a bundle of fiber to make the spider like material. and the material can take some weight, and then we have studied all these spectroscopy techniques, how the material pack in the wave, and we figure out that it is actually the anti-parallel beta sheet stacking that helps to make this material and make the spider silk and spider web. And we have published that in a chemical communication paper. Next, we have developed a hybrid material. So the left-hand side, left part, that is the peptide, diphenylalanine. Just in last talk, Professor Maiti talked about this peptide, diphenylalanine, very important moiety. And we have connected with this diphenylalanine, the post material, that is the polyoxosiloxane. And so we have prepared this compound 1, which is an organic inorganic hybrid material with the diphenylalanine and polyoxosiloxane. And we have studied all the solution phase spectroscopic techniques and solid state IR and all these things. And we confirm how the material self-assemble through intermolecular hydrogen bonding interaction, hydrophobic interaction, Van der Waals interaction, pi stacking interaction, so all the non-covalent interaction. And we figure out that the actual stacking is in anti-parallel beta sheet stacking, so the molecules are self-assembling with each other. And then we have studied the material with scanning electron microscopy, and we found that when it is only dipeptide, diphenylalanine, the compound form very nice hexagonal nanotube structure. And when it is only the polyoxosiloxane, the compound is fine cube structure. But when we mix them together, the compound is now a microsphere structure, a microsphere morphology, the compound adopts. And now we have taken a simple paper, and we have coated this paper with the compound 1 solution in dichloromethane. And what we have seen that the paper is now not wetting by water or moisture. And so if we now fold the paper has mechanical property, it's gain mechanical property, so it can unfold itself. And we have studied the mechanical properties, and we found that the mechanical properties actually increases several fold from the original papers. And we have studied with atomic force microscopy, and we figure out that on the surface of the paper, so there are this microsphere that's self-assembled on the surface of the paper. And we have studied whether the paper can resist the growth of bacteria or not. So we have studied with E. coli, and from the left panel you can see that the paper coated with the material, when it is underwater, it resists the formation of bacterial colony on its surface. So we made a paper, we transform a paper with the coating of the material to bacterial resistance. So we can use this kind of paper for packing purposes. And now this is a very interesting experiment. So with very low cost. So this is the iron nail, the raw iron nail, which are prone to rusting. And we have coated a half portion of the iron nail with our compound, and rest portion of the iron nail is uncoated. And we put that iron nail in water for overnight. And what we have seen that the uncoated part of the iron nail got rusted, whereas the coated part of the iron nail, nothing happened. So now I can say that I can protect any raw iron from corrosion. And we have further studied this with sodium chloride solution potassium chloride, KBr or NaBr. So we have tried to figure out if there is any salt effect, and we found that that salt do not have effect on that coating, whether the uncoated part is going to be corroded very fast. Even we have tried with HCl, and you can see from this panel that when the iron nail was put in the HCl, the uncoated part it has drastic effect on treatment with HCl, but the coated part is intact. So our material can protect the iron from acidic corrosion as well. And then this is a silver artifact. So believe me, this is a silver artifact. Actually, one of my students in a teacher's day gifted me a silver pen. So I just take out the clip of that silver pen, and we have coated again half portion of the silver pen with our material, and the rest half is free. And we just put it in chamber of Ag2S. So all of you know that if we use silver ornaments due to presence of hydrogen sulfide in air, so after a few days the silver ornament are going to be blackened by formation of Ag2S. So we have done that same thing. We have just put our material in a hydrogen sulfide chamber, and we found that the coated part is intact, but the non-coated part, it's the black things forms. And finally, we have used this material as a fire retardant system. So it is already reported that polyoxosiloxanes are fire retardant material, so they can reduce the flame. And when we just put our compound on surface of the matchstick. So for this experiment, we have chosen matchstick. So half of the wooden matchstick we have coated with our compound, and rest half is free. And so we have coated matchstick with without any coating. So that is the first row. And then with diphenylalanine, the peptide, that is the second row. Only the polyoxosiloxane, that is the third row, and finally our hybrid material, that is the fourth row. So what's happened when it is without coating, the matchstick completely burnt. When it is coated with the peptide, again the matchstick completely burnt. When it is coated with the polyoxosiloxane, the flame reduced, but again the matchstick completely burnt. But when it is coated with our hybrid peptide, the flame reduced as well as it stopped the flame. So we have applied for patent for this material. We have published this material, and this was highlighted in the Hindu, the newspaper. And we are now developing some valuable materials, some abrasives, including these systems with a Chennai-based company. And okay, so this is another example where you can see how it is interesting that simple chemical can convert it to a very interesting material, and that can protect from environmental pollution. So we know that due to this industrialization, so lots of heavy metals are nowadays coming in the water. And so the removal of heavy metals and other pollutants like this arsenic, fluoride from water is very, very important. And also due to this oil tanker and all this oil business, and for sometimes some accidents, lots of oils are going in water, basically on the sea water, and that damaging the sea ecosystem. So we need to remove that oil from seawater efficiently. So how we can do that? So for that purpose, actually we have developed a Juiter ionic material. So Juiter ionic material, that means they are both positive charge and negative charge. So the positive charge will attract the negatively charged anions from water and remove them from water. And the negatively charged part of the Juiter ionic system will attract the cations, the metal ions from water and remove them from the water. And out of that, we have introduced two hydrophobic functional group. So that will attract the oil or organic hydrophobic material and remove it from water. So the synthesis is very simple. So we have this nitroaromatic compound 2,4,6-dinitrophenol picric acid. So we just add picric acid with this DCC, dicyclohexyl carbodiamide. And so once you add this nitroaromatics with DCC, a very nice color will appear. And this compound is the Juiter ionic material to do this thing. And so we have studied this compound with all these solid and solution phase properties. And we figure out that the compound is actually forming a complex with fluoride, and it can remove fluoride from water. And again, when we have studied with metal ions, we figure out that the compounds can attract the metal ions from complex with metal ions, and it can remove the metal ions from water. So we have developed a system where we have FeCl3 solution, that iron solution in water, and we treat this with our compound, and after that we have filtered that solution. And what we figure out that there is no more iron. So the compound can completely remove iron from water. And this is actual drinking water from the campus. So from ISAR Kolkata campus, we have collected the tube well water. And if you keep that water for some time, after 1 hour, there is little bit yellowish color due to presence of iron in the water. And so if we treat this with our compound and we make a filtration, we'll get and water free from iron. So we have tested also for nickel and copper and other heavy metals, and we figure out that our compound is able to remove all these hazardous metal ions from water. And finally, so to remove the oil or organic material from water, we have coated a sponge. So that is basically we use to clean the utensil in our kitchen. So that is the kitchen sponge. And then we have coated that kitchen sponge with our material, and we just dip it in the contaminated water. The water contain oil, and we surprisingly our coated material coated sponge is taking only oil out of oil water mixture. And we have used this as a technology to separate oil from oil water mixture. So this is the oil water mixture. So we have used a sponge here. The sponge is coated with our material, and now we have also used a vacuum line with the sponge. And when we dip this sponge with the oil water surface, the sponge is collecting the oil from the oil water mixture, and with that vacuum line, we can collect the oil in a separate place. So we can separate the oil and water effectively. And this was highlighted in Chemical and Engineering News. We have published this. We have applied for an Indian patent. And with the Murugappa group, we are going to further utilize it in industry, basically in the car industry, that technology to separate the oil and water in the car cooling segment. And we have also developed a filter for drinking water using this technology. So now I will discuss about an in-field selective naked eye detection of 2,4,6 trinitrophenol. So that's an explosive material. And there are thousands of explosive detectors, but we are going for one robust system that can detect in solution, in solid, and in gas. So for this purpose, we have developed a series of peptides and a library of peptides. And from the library of peptides, we figure out that a peptide that contains tryptophan, tyrosine, and alpha amino isobutyric acid is a very robust structure. So there is a beta-turn structure inside, and then there is very strong pi-pi stacking interaction, T-type pi-pi stacking interaction that makes the peptide very robust. And if we just change the peptide sequence from tyrosine, tryptophan, and AIB, actually this robustness lost. And so with this peptide, we just coated with the paper or aluminum sheet. So that paper is now in touch with the 2,4,6 trinitrophenol, the picric acid. So immediately under 366 nanometer UV light, you can see when the two compounds, the peptide and the explosive, they contracted, they form a complex, and it turns black. So if there is a trace amount of compound, even in a fingerprint, so you can figure out that presence of explosive using our system. We have tried with solid one also. So we have just mixed our peptide with this picric acid, and after mixing, within few minutes, so a orange color appears. So what you can, what is visible in naked eye, and you do not need any sophisticated fluorescence technique or any ultraviolet ray or anything else, but just seeing by naked eye, you can detect whether this nitro explosive is present there or not. Or even we have developed a paper strip coated with our peptide, and if you just spread the nitro aromatics, the explosive on the paper strip, after few minutes you will see whether the nitro explosive starts the peptides, it's converted to a brown color. And also we have developed a system where we can detect the nitro aromatics in gaseous state. So, and in this year we have just published these results. Okay, so now I will talk a little bit about gel. And so all of you know that gel is a semi-solid jelly-like material, and that contain and entrap huge amount of liquid and solvents. And we tested gel by inverted test tube method. So that is the one of the method to test the gel. And gels are very important scaffold. So for energy transfer, for drug delivery, for cosmetics and tissue engineering. So, but generally, the people use the gel from polymeric system. So very big polymeric chain, they can fold three-dimensional, and they can make the network structure and interrupt the solvent and form the gel. But we are interested in supramolecular gel. So that is the gel makes from the small molecular building block by self-assembly process. So why? Because we can play with the building blocks, we can make diversity in the building blocks, and we can play with the intermolecular interaction and also with the morphology. More interestingly, that supramolecular gels, they are we can disassemble them, but that means they are reversible. So we can make them stimuli responsive. So only the thing, the force is that the supramolecular gel are not as much as physical strength like a polymer gel. Okay, so there are very famous review articles on supramolecular gels from small molecules. So if you are interested, you can see this one from Professor Shantanu Bhattacharya or Professor Jonathan Steed or Andrew D. Hamilton Vijaya Ghosh. So they are very nice review article on supramolecular gel. So for supramolecular gel, we need the building block. So what kind of building block? Acyclic peptide that we can use as a building block. So there may be dipeptide, tripeptide, tetrapeptide like that. Or we can use discotic peptide or peptide mimetics. And with this building blocks, so we can use different stimuli like thermoresponsive, sonication, photo, or chemoresponsive. So this we can use as a stimuli. And so this is an example where we converted a hydrophobic material by a thermoresponsive gel, and we converted it to a porous material that can use to remove toxic chemicals from solid and solutions. And yeah, I will emphasize little bit on this slide. So this is the discotic tripeptide where what we are talking about, and from this chemical communication paper by Boutelier group, it is clear that this discotic tripeptide that can form a six-fold dimer, six-fold hydrogen bonded dimer, or a three-fold hydrogen bonded columnar stack. And basically the Meyer group, they have used this kind of discotic tripeptide, and they explored many things, including the self-shortening, the liquid crystallinity of the discotic tripeptide, and so on. And so what we have used, we have made two discotic tripeptide, one with this cysteine containing compound and another with tyrosine containing compound. And what we found that the tyrosine containing compound failed to form gel in organic solvent, whereas that cysteine containing compound, it's formed nice gel in organic solvent. And then we started to figure out what exactly happened. So why one formed gel and why another failed to form gel. And with all these spectroscopic studies, we came to know that actually their packing pattern is different from tyrosine containing compound to cysteine containing compound. We have crystal structure of both the compound, and from the crystal structure, we confirm that when it is the cysteine containing compound, the compound actually forms a three-fold hydrogen bonded columnar structure, and that helps to make the fiber entangle and form gel. But when it is the tyrosine containing compound, uh, when it is the tyrosine containing compound, again there is a power cut. I don't know whether if I am audible or not. Okay, but when it is a tyrosine containing compound, due to this very large tyrosine functionality, so there is steric inhibition. And so now the three tyrosine moieties are not in the same plane with the benzene ring. So three tyrosine moiety is now out of the plane of the benzene ring. And that's why this compound failed to form a triple intermolecular hydrogen bonding structure like this, rather than it forms a hydrogen bond with 8 other molecules to make a cage-like porous structure. So this is the self-assembled structure of these two, and we have studied with atomic force microscopy that the compound containing tyrosine is making a porous morphology. And also we have studied using this gas absorption study, and we figured out that when the compound is porous, it can absorb up to 150 cc nitrogen per gram of compound, which is quite high for an organic compound. Okay, so due to lack of time, I am skipping these things, and well, So we have made also sonication responsive gel, and we have used that sonication responsive gel for other purposes to make the compound with dye and all these things. So I can skip this.
Hello, sir. Hello.
Devasis sir, your voice is not coming. Hello.
Yeah.
হালদার সাহেব আপনাকে কথা শোনা যাচ্ছে না, বোধহয় ফ্রিজ করে গিয়েছে। somehow it looks like it is hanged.
Connectivity is not there, I guess.
I think power. It's need power cut.
Yeah.
So, Taposh, am I audible?
Yeah. Yeah, sir. You are
Yes,
audible
now
and
you're
visible.
back. You are back.
Yeah.
Your voice is back.
Okay. So I am sharing my screen.
Yeah, sure, sir.
Okay, so we have developed a chemo-responsive gel. So the material that can form gel only in presence of potassium hydroxide and in a particular solvent composition.
স্যার আপনার স্ক্রিনটা আসছে না, একটু দেখবেন?
কিন্তু স্ক্রিন তো আমি শেয়ার করেছি।
Okay,
yes,
maybe
sir, coming, sir. Due to low bandwidth,
Yeah.
it takes time, sir.
okay, okay, fine.
It's
Then
in
it is
the process.
yes, yes. Now
Yeah,
এখন
yeah,
দেখা যাচ্ছে, এখন দেখা যাচ্ছে. Thank you. Sorry.
Okay, yeah, so there are 2 times power cuts, and I think probably that's caused a lot of this inconvenience. Okay, so we have made the gel, and the gel can form only in 1:9 water and methanol in this composition in presence of 5 equivalent potassium hydroxide. And we have tried with other composition. We have tried with potassium carbonate, lithium hydroxide, but they fail to form gel. So we need both the potassium and hydroxy, both the ions, to form the gel in 1:9 ratio water and methanol. And we have tested the gel with all these rheological studies, and so it is a nice gel. And with the step theory experiment, so it's from that the gel we can reverse. And so we have studied the gel, and the gel bar you can handle with naked eye, and you can make the gel in any shape you want, and you can make the gel in pieces, and you can color your gel using organic color, and so you can combine the gel slice together and you will get back your gel bar. So that means that the gel is highly dynamic in nature. The fibril formation in the gel is highly dynamic in nature. And we have studied with these FESEM studies. So here we figure out that the fibers are present in the zero gel, the dried gel. So what's the use of this gel? So we have used this gel as a fuel. So you don't need any particular or specialized burner or anything else. You just add little amount of gel on any surface, any glass or any iron or tin vessel, and then you can get heat out of that gel using fire. You can fire that gel. And once the material burn completely, you will get some powder. Again, you add 9:1 methanol and water. You will regenerate the gel. So you can use this for multiple. And so we have also used these techniques to remove little amount of organic solvent from water. Basically, the methanol or ethanol, if it is present in water, you can convert it in gel and then take it out from water. And so the gel is very easy to handle. You can put it in any kind of vessel, container, and you can easily handle it. And just using this thing, you can get sufficient amount of heat to make a candle-like material. You can make a Diwali out of this. You can use this gel for cooking purpose, or you can use this gel for outdoor heating, or you can go for a gel-like dinner with this gel material. And so we have published that in Journal of Material Chemistry. Yeah. And recently, we have developed a white light emitting system from a supramolecular organic inorganic hybrid gel. For that, we have used a dipeptide, that is the phenylalanine and valine containing dipeptide, a CDSE quantum dot, and a dye, that is LD700 perchlorate. So when we mixed this dye and the quantum dot in a particular ratio with this peptide gel, we found that hybrid material is emitting white light. So we can use this material for white light emitting purpose. And we have published this in Langmore last year. Okay, so our current goal, so this is the last part of my talk. I'll take hardly another 4-5 minutes. Our current goal is to minimize and or to eliminate solvents in our polymer or peptide control reactions. So this work, I was impressed from this Nature publication by Brookhart Group. So what they have done, they have made an iridium complex. And so that iridium complex, there is a small pore. And that small pore only can absorb ethylene and hydrogen. But once the ethylene and hydrogens are inside the pore, the iridium acts as a catalyst, and now the hydrogenation takes place and it converts to ethane. And as it's converted to ethane, the ethane is bigger in size. This is coming out from the system. So with this, we thought, can we make a nano reactor like a micro reactor? So you all know about micro reactor. So that is a device with 1 millimeter dimension channel, a confinement, and there is pumps. And so that is the glass channel for micro reactor. So your reagent is in solution state in liquid, and the reagent is pumping inside this micro channel, and inside the micro channel the reaction happening, and the reactions are very specific, and it's the energy efficient, high reaction speed, and it's very safe. And so we are thinking, can we make a molecular system like that? So we are thinking about a molecular reactor. Dimension of the system will be in the nanometer range, and confinement, it's a nano channel. So what is our plan is that, so we have a nano channel, we will load different reagents in the nano channel, and then there will be reactions, and we will get the product. So the channel range will be in the nanometer dimension, and that will appear from a supramolecular system, and the system will be valid for liquid gas or solid gas system. So advantage of that kind of system will be we don't need any solvent. The system will be eco-friendly, energy efficient, and highly selective. So actually, in chemical labs, so when we are doing some chemical reaction, we are using a lot of solvents, and then purification purpose, we are using silica gel, again lot of solvents, and after that we are producing huge amount of exposed solvent and that exposed silica gels or other chemicals. And obviously we are not dumping these outside of the planet, so we are dumping somewhat in the planet. So we are increasing the polluted material day by day from the chemical laboratories and industries as well. So that's why our plan to reduce the amount of solvent in the by using this molecular reactor or nano reactor. So we have designed a peptide for this purpose with 4 phenylalanine and 1 alpha amino isobutyric acid at the center. So we have a solid state structure of that peptide, and what we found that the peptide forms a 3-10 helical structure, and that aromatic functional group from the phenylalanine that actually make a pi channel, and that is our targeted supramolecular channel to do the chemical reaction. And so we have able to load toluene in that pi channel, and we have crystal structure of that, and we figure out that yes, the toluenes are there inside the pi channel, and we have able to load aniline in that channel, and again we have crystal structure conclude that we can load aniline in that pi channel. And so what kind of reaction we can do inside that channel? So first one, we have tried with the halogenation reaction. So for halogenation reactions, we need a halogen carrier, that is a catalyst. But here we do not need any catalyst. Just by incorporating a halogen inside the confinement, we can react aniline with the halogen and do the halogenation. So first we have started with a bromination, but the crystals got ruptured after bromination. Crystal got ruptured after bromination. Our nano reactor got ruptured. And we are very upset, but finally we have gone through mass spectroscopy analysis, and with that we figure out that instead of monobromination, it is actually tribromination of aniline, and that makes a bigger molecule, and that's ruptured our nano reactor. So okay, we have tried with iodine next time, and this time we figure out that our system is working. It's the monoiodination take place. That's we confirm from mass spectrometry. And also we came to know from the mass spectrometry that our peptide, the nano reactor, though there are 4 modes aromatic system, no iodination take place on that aromatic thing. So our peptide is working only as a platform to facilitate this reaction inside the nano channel. And so for iodination, now there is a question. So in which position, if it is a monoiodination of aniline, whether it is ortho or para position. So this is the crystals we have with the aniline, and then after exposure with the aniline, it's turned red color. And what we figure out from X-ray structure, that it is the ortho aniline iodination take place with the aniline. And this is due to particular orientation of that aniline in the nano channel. And now we are thinking, can we do other reactions inside this nano channel? So probably it is not in solid state, but probably in solution state where the channel is intact, but the reaction can take place inside the channel with better yield. And we have tried the Diels-Alder reaction, and we found that that nano channel is increasing the yield of the Diels-Alder reaction significantly in this nano reactor. Also, we have done this Morita-Baylis-Hillman reaction inside the channel, and again we have found that this rate of reaction increasing significantly. And we have published this in ACS Omega 2019. So what is next? So that is the dream. So can we figure out an assembly line like a car assembly line? So where we can just screw or nut and bolt different parts of the car and make a complete car. So I am dreaming about the assembly line for a chemical reaction where we can combine different functional group in a nano reactor without much solvent, without much exposed silica gel and other pollutants. So with that, I will conclude. So these are my books that are available in Amazon. So about the synthesis of amino acids and analog and smart functional material. So if you are interested, I will thanks my research group. So the students who has actually done this research, without their help, it is not possible to this amount of work. And so these are my present research students. So these are my former research students. So they have helped me a lot to do this research. And I will thanks the financial support. Obviously, that is a big part of research. So I thank CSIR, DST, Alexander von Humboldt Foundation, and ISA Kolkata for financial support. And finally, thank you very much for your kind attention. And I am very sorry for that inconvenience happened due to power cut in our institute for 2 or 3 times. Thank you very much.
Thank you, sir. I'm audible, I guess, right?
Yes, yes.
Okay. Okay. Thank you, sir. It was a wonderful session, thoroughly enjoyed by me personally, and surely all the participants were enthralled by your informative and insightful presentation. And the deliberation engaged the participants for the whole session, I believe. And it was pleasure listening you on such concise yet insightful, illuminating presentation on the topic of smart materials, peptidic smart materials, which include their properties like to prevent the corrosions, remove oil or ions from water. That was very important significantly, and the fluoride removal, iron removal, the sponge coated material to remove the oil from a mixture of water and oil, and supramolecular gel, the discodic peptidic materials for cage materials to storage of gases, and so very many things you have discussed elaborately in a lucid manner that will help the participant, be it the students of our community or the researchers or everyone. Thank you very much, sir. And I truly believe the participant will be benefited very much. And I wish that your dream to have the assembly line with all these materials and for the chemical reactions with less hazardous conditions will come true. And we all hope for that because it's for the benefit of the researchers and the community as well. So thank you, sir. May I now go to the question answer session? And I think we have a couple of questions in the chat box. It's from a couple of questions from Shatarupa Bhaumik. I think she is the master students in our in-house campus, MSc in Applied Chemistry student. And she has queries regarding why does the photoluminescence occur when heavy metal is attached in any nanocluster? The first question. The second question is how nanomaterials help in lubrication. Sir, if you can answer the question.
Yes, so I think she is talking about the phosphorescence,
Yes.
the photoluminescence means. And so when this is a heavy atom or a heavy metal, it attaches with a chromophoric system. So that is due to this back donation, the phosphorescence take place. And so about the nanomaterial that help in lubrication, yes, of course, we can use that nanomaterials for lubrication. And actually, for that purpose, you need to prepare the nanomaterial, or you need to design the nanomaterial that can work at high temperature. Because most of the lubrication or lubricant we used at high temperature. So if you prepared a nanomaterial with the very small molecule and metal nanoparticle, then there is always a possibility that small molecule may decay in the very high temperature or even in moderate temperature. So that's why if the design of the nanomaterial, if you want to use it as a lubricant, is very, very important.
Thank you,
Would
sir.
carbon fullerene buckyballs work, sir?
Yes, you can use that fullerenes or buckyballs as a lubricant, but for small molecules, it is difficult, because for buckyball or fullerene, it is the carbon 60, and so it is a huge molecule. It is a big molecule.
But still smaller than conventional lubricant.
Yeah, that's true. That's true. That's true. That this is still smaller than conventional material, but still you can use that fullerene or buckyball in the lubricant. But for nowadays, there are many nanomaterials, basically the metal nanomaterials that you can use as a lubricant. Only the thing is that you have to use the coating judiciously. So you have to use the stabilizer judiciously. It should not be a very small one.
Thank you, sir. So due to time constraint, maybe we will not be have much questions, but I can't resist myself of having a query, though we have we are running short of time. Sir, regarding the discotic cage materials or discotic peptidic materials,
Yeah.
Is it possible to explore that in terms of the liquid crystal point of view for those materials? Because
Yes,
they are
of course.
potentially, it seems very useful to form those kind of materials, I guess.
Yes, of course. So for most of these discotic materials, people have used for this liquid crystalline properties. So only very few cases where we use it for as a porous material or do something
Exactly.
else as a gels or whatever it is. But mainly the discotic materials are used for liquid crystalline properties.
Yes. Okay. Thank you, sir. I have a couple of more queries, but I will personally have interactions with you later on. And I hope, as I also work on the liquid crystal field, so maybe we can collaborate very soon
Okay,
in near future.
of course.
And
So
definitely, that
yeah,
can
you
help.
can come back to me at any time. Okay,
Sure,
thank you
sir.
very much.
Sure. Thank you, sir. And may I now request our head of the department, Dr. Radha Vallabh Bhar, sir, to kindly deliver the vote of thanks and for formal closure of this webinar. To you, sir.
Thank you, Dr. Ghosh, for giving me opportunity to offer vote of thanks. I am very happy that throughout the whole zone or time I was here, and here two eminent speakers has enriched us a lot in different areas, particularly in nanomaterials. First of all, I want to thank our Vice Chancellor, Professor Dr. Soikot Moitro, because he is the initiator for organizing such a nice webinar. Because when COVID pandemic or COVID-19 came, at that time, we are also spellbound that what to do, what next, what will be the academic continuation, academic activities. Then in that case, our Vice Chancellor has given a good guideline. Before starting the pandemic, he has given us guideline that we should start digital platform, we should use digital platform. And from then onwards, we started to use different platform by getting initiative from his mind. And in the webinar also, I have seen that almost all the webinar he tried to come and he inaugurate or give his speech with very knowledgeable person, because all the area he has given some input, and here also he has initially given some area about the tools and techniques and how nanomaterials came and what is the way by which it came to a different field. Different field means now nanomaterials, nanotechnology is used in almost all the fields: material science, biological science, whatever what not, in device making, all the area. So he is the main inspirator of us. I thank to our Vice Chancellor on behalf of our organizing committee, on behalf of our department, and on behalf of our school, so that and we hope he'll always be there with us. Now, next, I must thanks to the speakers. Initially, Dr. Dilip Kumar Ghosh, Professor Dilip Kumar Ghosh, he started his speech with the very beginning, so that those who are particularly participants, beginners, they have got a good exposure that what is nanomaterials, what is from that, how nanomaterials is important, means how nanomaterials is giving different properties, and its properties is changing whenever you are coming small in size, then gradually we are reducing with the different, we are losing or generating different types of new properties, and how that properties can be utilized for different device purpose or different purposes. So he mainly given some idea about some organic compounds, and organic compounds can also be used in different device for how it can be used for device, means RAM and other type of electronic device as well. So that is a good idea about our participants, I think, particularly those who are beginner. And that area and different types of application, he has given different types of different area of applications in this field. And accordingly, I think he enriched all of us as a very big way. And I give my sincere thanks to him on behalf of the department, on behalf of the school, and on behalf of the university. So I hope in future also he will be with us, because our university is relatively, because our university is to some extent in backside, particularly tools and techniques, because for nanomaterials, it is necessary to get help from different tools and techniques is very much needed. When it was started from the Vice Chancellor, yes, they have mentioned about the atomic force microscopy, FESTM, STM, fluorescence spectroscopy, so many gadgets, all both the two speakers, eminent speaker use. And from that, I can understand that how type of tools we need if we want to go for nanomaterial study. So for that, we need collaboration from all the institutes. I hope they will help us in future. Our university students, university academicians can get help from them, as well as knowledge, as well as some sort of other form, so that we can enrich ourselves, our university can enrich the students and other communities. So thanks to Professor Maiti for giving his valuable time and his sharing his knowledge with us. Now our eminent second speaker, that is Professor Devashish Haldar, is very much uh, knowledgeable person. He has given very good idea about the synthesis of amino acid, which is very important component and very much needed. How to, obviously it is available in different materials, but how we can artificially generate it. He has given some good idea about it. Not only that, here it shows us a different application of peptide, hybrid peptide, and by using that, what are the different applications, and that area can be utilized for human purposes. He has given a very good exposure to our participants and also us also. So enriched us also. And so we must give our sincere thanks on behalf of our department, on behalf of our school, on behalf of our university. And we hope ISAR is very close to the university, and in future also they will help us in different way so that we can enrich, we can train our student in future generation student, and our university can get some exposure in different coming uh, recent technology or recent ideas, innovative ideas. Now we'll go for our director. Director, Professor Samajdar, he is always with us. Whenever we face problem, we go to him, and he is in organizing different webinar also. He is with us, and we are very happy that here also he started from the what is nanometer, what is the position of the nanometer, from kilometer to femtometer, ultimately where nanometer is, and from that, from Richard Feynman to and a quote of so many eminent scientists, how this nanotechnology came, he mentioned thoroughly in his initial talk. So I must convey my sincere thanks to him on behalf of our department, and he is our school director, and all the time with he is with us and encouraging us and giving different direction to us to continue our different program. So thank you, our director. Then obviously main component of this webinar or any webinar is the participant. They are also very enthusiastic, and almost all of them still it is listening. It is very good that already lunch hour started, but still they are continuing, and I hope this enthusiasm will give some benefit, because both the speaker told a very lot of things, and if they can absorb these things, so they can also can think, and their young mind can think in new way how they are thinking to develop different types of new materials. So this is so I thanks to all participants on behalf of the department, on behalf of the school, on behalf of the university, those who are particularly outside the university. They are initially our convener, Dr. Ghosh, already welcomed him, but I want to also express my sincere thanks to him also. And then I want to convey my back unseen worker, because for organizing any program, there are some front side worker is there. Those who can see, who can understand that these are the people involved over here, but there are unseen worker, so many unseen worker. And other colleagues of my departments, and they are also have done their some input, given their input, and also particularly the webinar team, Prem Kumar and his team has working a lot for each webinar from starting day, means when flyer is putting into the website, from then to up to the end of the program. He is always there. If any problem, they are sorting it out immediately and guiding us how to make this webinar without any problem. So that is we thanks to the webinar team of the university. So and throughout the program, he has conducted smoothly. No problem was there. So these are the. I also thanks to the other panelists, Dr. Bab, and obviously Dr. Convener is the main leader. He has done a lot of things on it. So on behalf of the department, I give him thanks, because he organized probably this one is the third one. Third one, first one, student seminar. Second, another one he has organized, not very far, only few days back. And this one is the third one. So it is a very thankful to him. We are thankful to him on behalf of the, he is also enriching our department, because good number of webinar organization is not an easy job. So that is also, he has done it, and thankful to him also. So thank you all.
Thank you, sir.
Already lunch hour is due. So it is better to stop it now. For I thank all, particularly we are enriched ourselves for the two eminent speakers, and my heartfelt thanks to them, and with the expectation that we will get support from them in the future. Okay, thank you all, sir.
Okay. Can I take a minute, please?
Sure, sir.
I would like to extend particularly the thanks, not just thanks, but the policy of the university is to not charge any registration fees from the participant, because we believe that educational experiences should be as accessible as possible. So it would not have been possible but for the graciousness and generosity of our distinguished speakers. So please, that is a point that I would like to mention. And also I would like to mention, particularly Professor, for our speakers today, Dr. Maiti, Professor Maiti, and Professor Haldar have been all the way with us, especially the Chemical Sciences Unit, to being part of the very active and very contributive member of the Board of Studies. So it is my duty as the director to acknowledge their contribution to the department, to the programs, and to the university as a whole. So that's on these 2 points, I would like to extend my personal gratefulness to them as well. Thank you.
Hello, Tapas sir, are you there? Hello?
I guess
Tapas?
Dr. Ghosh got disconnected or something.
Yes, sir, I think so.
Dr. Bagh.
Sir, Tapas
Okay,
sir
I am here.
was...
I am here.
Yeah, sir. Sorry for the interruption, sir. So it was, yeah. So, hello.
Hello. Okay.
Yes, sir, yes, sir, yes.
Okay.
Yes.
Okay.
I think
Now hearable.
it is time to close, isn't it, Dr.
Yeah.